Stripping down science. The Naked Scientists.
Hello, it's Sunday, September the 12th. Welcome to a brand new series of The Naked Scientists. We're kicking off with a look at your science questions too. Warren wants to know what would happen to his fish if he took it in its bowl into orbit aboard the International Space Station. What do you think? And does dreaming burn extra calories, especially if you go for a run in your dreams? That's what Farah is worrying and wondering about on our Facebook page. And John asks, if the world were made of glass, could we see through it? Plus, also on the show, we've got news of self-cleaning solar cells, a new way to selectively kill cancer cells, and how meteorites smashing into Jupiter are revealing what's actually lurking in the asteroid belt. Hello, I'm Chris Smith, and also here for this week's programme are Dominic Ford. Hello, Dominic.
Hi, Chris.
He's from our Naked Astronomy podcast, and our kitchen science guru, Dave Ansell. Hello, Dave.
Hello, and speaking of kitchen science, I've got a really cool experiment for you to try later on the show, which promises to be a breath of fresh air, and there might be a clue in there.
Thank you very much, Dave. If you've got a question you'd like us to answer, send your emails to chris@thenakedscientists.com, tweet them to @nakedscientists, or scribble them down on our Facebook page.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
And let's kick off, as we always do, with a look at what's hot around the world from the world of science news. Dave, what have you got first?
A new form of self-cleaning solar cells has been developed. Now, many of the sunniest places on Earth are also deserts, obviously, and therefore the best place to put your solar cell is both very dusty and also very, very short of water to wash the dust off your solar panels. This can seriously reduce the efficiency of the system. Not only is this a problem on Earth, but the Mars rovers Spirit and Opportunity have been slowly losing power, and if it wasn't for the occasional random Martian mini whirlwind, they could have conked out years ago. Now, Malay Mazumba from Boston University has been working on this problem. In fact, he was working on lunar landers because the moon is especially bad for dust. He may have come up with a particularly neat water-free solution which will work on Earth as well. The idea is to cover the solar cell with small transparent electrodes and occasionally apply very high voltages to these electrodes, thousands of volts. These voltages are arranged to form waves moving across the panel, which charge up dust, push it away gently, and then they sort of levitate and get pushed off the panel.
So do you need a moving sort of current then in order to make the dust move? Because otherwise, why wouldn't it just lift up and come back down again?
There's very, very small currents involved, but you do need to move these kind of areas of high voltage a lot across your solar panels. They get picked up and slowly moved across the panel. They reckon that they can shift about 90% of the dust on a panel in 60 seconds. And the energy is very, very small because although there's high voltage, it's very, very low current.
Because it has been a major problem. I know you mentioned Mars, but they're having to over-engineer more power capacity into the panels to compensate. And this means if you had a cleaning mechanism, you could have smaller, lighter space probes and things that would go for longer with fewer breakdowns and less of this dust problem.
And even on Earth, you get more power for your money.
Indeed. Well, talking about the issue of using alternative energy and that kind of thing, there's a really interesting paper in the journal Science this week, which I think is one of the most interesting papers that's actually emerged this year. And in this paper, which is by Stephen Davies and his colleagues, they're at the Carnegie Institute, they're in Stanford, California, they have asked the question, we're all worried about climate change, we're all worried about whether or not it's possible to rescue the Earth from its fate because of the CO2 we've already put out into the atmosphere, but is it already too late? Or if we make changes now, can we turn this whole thing around? Is it yet game over or not? Now, they've approached this in a very interesting way. What they did was to say, well, if we take all of the energy infrastructure and the traffic and the population we have on Earth at the moment, we know how much CO2 that makes. If we freeze that in time and therefore say, let it live out its lifetime, because they know that a coal-fired power station lasts about 40 years, a car is on the road for about 17 years, people are around for 60, 70 years, and so on. We know, therefore, how much CO2 that lot, the Earth as it stands at the moment, is going to produce. And they come up with a number of about 500 billion tonnes of CO2 between now and 2060. They can say that will warm the Earth up by about 1.3 degrees C compared with pre-industrial levels when we started to really churn up the CO2. That's about 0.7 C hotter than it is now. That, they say, is what happens if we just don't build any new stuff. What will that do to CO2 ultimately, though? Well, according to their model, this will mean that the Earth stabilises with a CO2 level of about 430 parts per million. It's currently about 390. That will mean that that's a long way short of the 450 parts per million that scientists say would be the point of no return. In other words, when we think the climate would go into a sort of positive feedback cycle and the game would be over, it would be unrescuable. So in other words, it's not the present infrastructure and it's not the present population that are the biggest threat to the Earth's future. It's actually, according to the researchers, what we're going to build next. So in other words, we have to pay particular attention to making sure that we roll out carbon-free energy infrastructure in the future, as Stephen Davies explains.
What we'd like to emphasize is that what's built isn't necessarily going to put us over these critical thresholds, but we need to really concentrate on building the right things going forward. I think one implication of this is that it might suffice to get existing coal-burning power plants, for instance, to commit to their scheduled shutdown dates and not to spend a whole lot of political capital trying to decommission those things early, because it seems like they are not the ones that are going to cause the worst impacts. Well, I would say that the takeaway is that there's a kernel of hope that we can still turn the ship, that the worst problems are yet to be built. But that said, I think we qualify that by saying that there's still a lot of inertia in the system and that it's going to be very difficult to turn that ship. So we don't want to downplay the effort that it's going to require to ramp up carbon-free energy technology.
Stephen Davies talking to us there. Dominic.
Well, a paper published this week in the Astrophysical Journal presents the first direct observations of small asteroids in the outer solar system. And this is a story that began back in June, when a couple of amateur astronomers on different continents were pointing telescopes simultaneously at Jupiter, and they saw a flash in Jupiter's atmosphere.
Not a naked scientist flashing on Jupiter. What did they actually see, though?
This was a pulse of light which lasted for about 2 seconds. It sounds like a small thing, but they knew that this was odd, this was different, and they reported it. And since then, astronomers have been really working to explain what could have caused this flash. And they think it was probably the impact of a small asteroid into Jupiter's atmosphere. And the research published this week has actually got as far as producing quite a precise estimate of the size of this asteroid, which they think was about 10 metres across.
That's amazing. It's a Jovian shooting star, for want of a better term, and
exactly.
You can use the flash to size the object. Is that by working out how bright it is? So you know roughly how much light it must have given out, given the distance between us and Jupiter then?
Yes, the larger the object, the brighter the flash it produces, and they have got images of this flash. They know how much light was there, and they can use models based on shooting stars in the Earth's atmosphere to work out how big this object was.
And why is that significant?
Well, the small size of this object is fascinating because there's never been a direct observation of an object this small that far out in the solar system before. We've thought these objects must be there because we know they're close to the Earth, but we've never actually seen one close to Jupiter. We've had no idea how many of these objects there are.
Well, that's an interesting point. Is it a one-off?
Well, this is fascinating because in August, another couple of amateur astronomers saw an almost identical event, a second event. So it seems probably these events have been going on several times a year, forever, and people have just assumed that you can't see them or haven't been looking for them, and so they've gone unrecorded. Now people know that you can see them, they're recording them, and probably in the next few months and years we can expect to see lots more of these events being seen. And that means we can start to understand the distribution of sizes, the distribution in space of small objects on the outer edge of the asteroid belt. And that means in terms of working out where the asteroid belt came from, we can constrain those models much better.
Which ultimately informs us a bit more about how our solar system put itself together about 4.5 billion years ago, presumably.
Yes, the leading theory is that a planet couldn't form between the orbits of Mars and Jupiter, although there's quite a big gap there because of the gravitational influence of Jupiter, and so you had this pile of rubble which never managed to form into a planet. This will help to constrain those theories.
And why are these meteorites only now appearing? Well, I should say, why are these asteroids only now beginning to impact on Jupiter, given that they've had 4.5 billion years of solar system evolution to do that?
The objects that we're seeing have probably been orbiting in the asteroid belt in stable orbits for a long time. They've perhaps had a close encounter with another object and been kicked into a different orbit, which has made them unstable and thrown them towards Jupiter.
Dominic, thank you. Well, also this week, scientists have made a big breakthrough in understanding a new way to tackle the problem of cancer. Of course, cancer is a genetic disease. Cells run amok in the body. They grow out of control. They ignore the normal growth constraints and tissue constraints, and they invade, damage other tissues and spread to other sites around the body. And they also chemically disturb your metabolism, which is all part of the disease associated with having cancer. One of the problems with treating cancer, though, are those very factors. They're your own cells, so how do you discriminate against them with drugs? And most of the drugs we do have just target cells that are growing very fast, which means that they also inevitably have side effects. Wouldn't it be nice if there was a way to selectively home in just on cancer cells and persuade them to kill themselves? Well, that's what Niles Pearce and his colleagues, who are based at Caltech in America, have published in the journal PNAS this week. They found a way to make it happen for at least some cancers. What they've done is to build what are called conditional RNAs. These are small pieces of genetic material called RNA. It's a genetic relative of DNA, but unlike DNA, which is two chains of genetic material, one being the mirror image of the other, RNA is just single-stranded. It's a single piece of genetic material. And when you put it into a cell, it can go looking for its mirror image counterpart in the genetic material. So what they've done is to produce these RNA molecules, one of which they term the diagnostic molecule, the diagnostic component, and this can be programmed to seek out specific and characteristic genetic sequences in the genome of the cell which are associated with certain cancers. And if this small RNA detects those genetic changes, it can then change its shape, triggering a second conditional RNA to unwind its structure, and it then recruits other of these small molecules and joins up with them, producing a very long sequence, almost in a chain reaction, of what's called double-stranded RNA. Now, you never normally see double-stranded RNA in a cell. It only happens if the cell becomes virally infected. And cells have evolved their own unique way to deal with viruses that infect them. They kill themselves. So when a cell sees this tract of double-stranded RNA, it's fooled into thinking it's been infected by a virus and it commits suicide. And what the researchers have been able to do is to test this strategy against 4 different types of cancer in the dish, and they find that they can achieve selective killing of the cancer cells only by between 20 and 100-fold compared with healthy cells. In other words, it's a bit like a genetic smart bomb that only goes off if the cell is cancerous. So does it work for all cancers? Well, unfortunately not necessarily, because some cells have evolved not to have this antivirus mechanism working in them, because that's part of the cancer disease. So it won't work for everything, but it does have several significant advantages, as Niles Pearce explains.
There are 2 crucial properties of the approach that would make a difference for patients if we were able to use this in humans. One is that we would be able to program drugs for a particular tumor in a particular patient. 2, these conditional chemotherapies would turn on selectively only in cells that contain the targeted cancer mutation. And so conceptually, this would lead to dramatically reduced side effects. So both of those properties would be fundamentally important to a patient.
Niles Pearce from Caltech talking to us earlier this week.
Thanks. And now for something completely different. Something which is perplexing physicists is why the fundamental physical constants are what they are. Why the speed of light is about 300,000 kilometres a second. Why the charge of electron is what it is. For that matter, are they actually constant? So this is actually boiling down to why does physics behave as it does, and is it the same everywhere?
Yeah, I was going to say, because when you say are they constant, there's 2 questions in that, isn't there? One is, are they constant as in one place all the time? And then the other part of the question is, well, are they constant here, but not somewhere else in space?
That's right. We know that they're pretty much constant, and everywhere we've done experiments, they seem to be exactly the same, but we're limited to the places we can actually do physical experiments to where we can get to, basically, in our solar system. The one thing which we can test in the rest of the universe is something called the fine structure constant. This is kind of the combination of the charge of the electron, the Planck's constant, and the speed of light, and measures how the electric field and quantum mechanics interact to create energy levels inside an atom. And it can be measured by looking at the spectra of atoms. So it's very great. It's great for astronomers. You can look at things billions of light years away. Now, John Webb and colleagues from the University of New South Wales have been looking at some of the most distant sources we can see. They're called quasars, active galaxies, billions of light years away. These are black holes accreting material. And in 2003, they discovered that the fine constants... And in 2003, they discovered that the fine structure constant appears to have increased about 1 part in 200,000 since the light left these quasars. But the study was only done in the northern hemisphere, so he thought he ought to do it in the southern hemisphere, and he's just got the results back from the Very Large Telescope in Chile. And they found something possibly even more interesting. The result was in the south, the fine structure constant was changing by about the same amount as you go back in time, but it was decreasing rather than increasing.
So, in other words, they're not looking at the same target in the north and south hemispheres. They're looking at different bits of the universe.
Yeah, because the northern hemisphere, you can only see upwards to the north, and southern hemisphere you can only see downwards, so you look at different bits of the universe.
So that argues that different bits of the universe are obeying potentially different rules of physics.
Yeah, it's very, very subtle, 1 part in 100,000, but yeah, it could be that they're obeying the laws of physics are changing throughout the universe.
What does that mean for astronomy? Because we've been making all these measurements about very distant, very far away objects and trying to understand very, very massive numbers and the structure of the universe. So if it obeys different rules in different bits of itself, A, how does that happen? And B, what does that actually mean in terms of our understanding of the structure of the universe?
Well, if these results do hold up, I mean, time will tell, but it could mean that lots of cosmology is based on the physics being exactly as it is now. So all sorts of things which they're deriving after one layer after layer after layer could be completely wrong. But it could also explain why the physical constants seem to be so ideal for our type of life here. Because if they're different all over the universe, then obviously there will be somewhere where it'll work, and this happens to be it.
And that massively increases the chances of us existing, really, doesn't it? It's not just so unlikely that we exist with these numbers the way they are. It's just that there's so many different rolls of the dice right across the known universe that somewhere you're going to get the right combinations of numbers to make a life like ours possible.
Yeah, in a big enough universe, there will be somewhere where life can thrive.
So what's it going to take to get to the bottom of this, to know whether this is, A, a real observation and holds true for the whole universe, and B, actually then what we're going to do about it?
Well, I guess they're going to have to do a lot more experiments, see whether it holds up. Probably different people will do it, attempting to test it in different ways, because this is essentially only one result. It might be some systematic error in their telescopes or something wrong. So basically a lot more physics over probably quite a few years.
Reacting to the world's best science. The Naked Scientists.
Now, also this week, EPSRC, that's the Engineering and Physical Sciences Research Council, funded researchers in Glasgow have been investigating how we respond emotionally to music and how this could lead to music actually being used in pain control, almost music on prescription. Sarah Castor-Perry has caught up with the researchers involved to find out a little bit more.
We are all musical. Every human being has a biological and social guarantee of musicianship. Everybody can learn to express themselves and communicate through music. Also, we are all musical in the sense that we all respond emotionally to music. When we listen to music, we are moved in quite profound and powerful ways.
So whether it's a soothing classical melody or a raging, angry rock song, we all have a hugely emotional relationship with music. That was Professor Raymond MacDonald at Glasgow Caledonian University, who's part of a project being funded by the Engineering and Physical Sciences Research Council to find out how music conveys emotion. The project brings together music psychologists like Professor MacDonald with expert audio engineers like Dr. Don Knox, who's been using volunteers and specially developed computer software to analyse a huge range of pieces of contemporary music to determine the mood and emotion that they express.
We try to classify and categorise pieces of music in terms of two axes, one of which is intensity and loudness, and the other one is valence or stress, negative, positive stress. So they look at the general overall loudness and activity levels in the music. And if they were, above a certain point, the music might be classed as being exuberant, or if it was negatively stressed, it might be anxious or frantic. And we analyse and extract lots of audio and acoustical parameters from the music and map the pieces of music onto those axes.
But what makes us choose particular pieces of music in different situations?
When we first say to people, this is what we're doing, we're classifying music emotion, some of the first comments you get is, well, I'll put the happy music on to do happy things and dance, and I'll put sad music on or relaxing music to do this. And really, it's much more complicated than that, and the music psychologists are really opening their eyes to how people actually interact with music. that relationship and emotional connection with music and how people use it for things like stress reduction and pain relief, if you will, is much more complicated than just using happy music for happy things and sad music for sad things.
And classifying each piece of music in such a detailed way is allowing the music psychologists to figure out exactly what it is in the music that makes us choose it for a particular situation, and how it can affect not just our emotions, but our physical perception too. Professor MacDonald explained to me how the project is building on previous studies carried out with his colleague Laura Mitchell.
Earlier work purely looked at people's preference. So what we initially found out was that listening to your favourite music reduced your anxiety perceptions and your pain perceptions. And we had a whole range of different types of music that was selected. Hotel California by the Eagles, Pachelbel's Canon, In My Place by Coldplay. And we originally suggested that there was no common structural features between these particular pieces. But Don's work, along with Scott Beveridge, has been able to show, or starting to show, how certain structural features of music are important in trying to predict their emotional effect upon the listener.
So although there is still work to be done, the implications of the project are really exciting. On the one hand, knowing how people respond emotionally to particular structures found in music could have important clinical applications in music therapy and using music for pain control. And also, for all those music lovers out there addicted to their MP3 players, it could herald a new way of classifying the music in your library and a new way of searching for that exact piece of music to match your mood.
So, in the future, you might find yourself browsing through the music store by mood rather than by artist. I also hope it doesn't usher in an era where people get sued for making people depressed because they played a tune that's known to provoke negative emotions. What a horrible thought. Sarah Castor-Perry was speaking with Glasgow Caledonian University's Raymond MacDonald and Don Knox. You're listening to The Naked Scientist. It's Chris Smith, Dave Ansell and Dominic Ford, and we're answering all your science questions. If you'd like to send us one, you can email chris@thenakedscientist.com. You can scribble on our Facebook page, or at Naked Scientist, you can tweet us. Now, Mike is on the phone. Hello, Mike.
Yeah, Chris, I'm calling from Cape Town. I've got a question for you.
Go on.
I'm calling about the effect of the gravitational pull of the moon has on our tides. As I understand it, the moon, when it's directly overhead, causes the oceans to rise, and thus giving us our high tide. And we experience that twice every 24 hours. But the moon, in fact, is only overhead once every 24 hours at the same spot. Now, what causes the second high tide?
Dominic, what do you think?
Well, Mike's absolutely right that it's the pull of the moon on the water in the oceans which causes the tides. And the moon is, of course, only ever above one point in the Earth at any given time. The effect is actually that the Earth is of a finite size and the water on one side is pulled fractionally more strongly than the water on the other side because it's closer to the moon and the gravitational force decreases with distance from the moon. And the water which is closer to the moon is pulled more strongly, and so it's pulled up into a tide. On the opposite side, it's pulled slightly less strongly, and so it's pulled down less strongly towards the surface of the Earth, and so you get a second bulge on the far side of the Earth.
So, in other words, there are two blobs of water on the Earth's surface. One closest to the moon because the water is feeling a force from the moon and you've got a bulge there. And then on the opposite side of the Earth, furthest away from the moon, because that water is further from the moon, it's being pulled less than the Earth is. So you've got a second bulge there. And at 90 degrees, you've got two dips, which are the low tides. Is that right?
That's exactly it.
So there you go, Mike. Thank you. Brilliant question. Dave, I reckon this is a good one for you to answer, actually. George says, he's coming by email, chris@thenakedscientist.com, if a bus is travelling at 100 kilometres an hour and you are at the back of the bus holding a bird and it flies towards the front of the bus, how fast is the bird flying?
Okay, this is essentially a question about relative speeds. Compared to someone standing on the ground, then the bird is flying at 120 miles an hour or something. Compared to someone in the bus, it's doing, say, 20 miles an hour. The important thing for the bird is the fact that it's going at 20 miles an hour because the speed the bird is moving through the air will affect how its wings behave and whether it can fly and things like that. So basically all answers are true depending on where you're looking from. But I think the most important one is how fast the bird's moving through the air, so 20 miles an hour.
So as far as the bird is concerned, the bird is going along at whatever speed it flies at. As far as an observer in the bus is concerned, the bird is flying at however fast the bird thinks it's flying, but a person outside the bus thinks the bird is flying at the bird speed plus the bus speed. Yeah. And this is where it breaks down with light, isn't it? Because if you did the experiment with light, that is not what you would see.
No, the bizarre thing about the way the universe seems to work is that if you did the same experiment with light, everyone would see it was going at about 300,000 kilometres a second, and everything else changes to make that work. So time and space will warp so as that appears to work.
And you need a warped mind to understand it. Thank you, Dave. Pam Giles is with us. Hello, Pam.
Hey, hello.
Welcome to The Naked Scientists. Fire away.
Thank you so much. My students and I did an experiment where we had water that was 117 degrees. We placed 2 containers inside in the air conditioning at 78 degrees and 2 containers of the same temperature, same quantity of water, 2 outside in the sun, 2 outside in the shade. We were expecting the water in the classroom to cool a lot quicker than the water outside. However, we were shocked to find that the water outside in 90-degree weather in the shade cooled about 4 degrees for 5 minutes, and it cooled a lot quicker than the water in the classroom that was only cooling off about 2 degrees for 5 minutes. And that continued for about an hour and a half. Then finally, the water outside and inside was at the room temperature inside and at the air temperature outside. Someone suggested it was evaporation, so we covered the tops the next day and redid the experiment and still got the same results. We're wondering, why is the water in the hotter air cooling quicker than the water in the cool air-conditioned classroom?
That's very interesting. The answer I was going to give immediately was evaporation, because the maximum amount of heat which some water loses is generally due to evaporation, and therefore if you've got wind blowing across the top, all those hot molecules evaporating off the top will get blown away quicker. You can get more evaporation, it's going to lose heat quicker. I would have thought the only big effect is going to be the wind, and it could just be that even just losing heat to the air around it is a lot faster if wind is blowing past something, because otherwise, if the air is stationary, the hot object just heats up the air around it, and then that insulates it from the rest of the air. If there's a wind blowing past, it will keep moving that hot air away, and so you can keep losing heat much more quickly. Certainly the only thing I can think of is that it's to do with the wind, but possibly due to conduction as well as evaporation.
Pam, well done. You've managed to rewrite the rules of physics in your part of the world. Thanks for calling. If you want to get in touch with us here at The Naked Scientists, Chris Smith, Dave Ansell and Dominic Ford, we're answering your science questions on The Naked Scientists. You can email chris@thenakedscientists.com. You can scribble on our Facebook page, or at Naked Scientists, you can tweet us. That's exactly what David Worley, 94, did, and he said, guys, would there be any evolutionary advantage to being a cannibal? What do you reckon?
I guess it depends what you are and how many diseases you've got that there are going around. So the big disadvantage to being a cannibal is that if you're eating something of your own species, it can get all the same diseases as you can, and therefore you eat them, and then you get all of their diseases, and then you die.
Yeah, that's exactly what happened to the 4 people in New Guinea who developed a disease called kuru, which was a prion disease, a bit like mad cow disease, but it was a human equivalent. And because it was a ritual for the women in the tribe to eat the brains of the dead relative when they buried them, there was an excess of women affected by this terrible neurological condition that came on all of a sudden, and the actual word means he who trembleth in the native language, because people got this BSE-like disease and they all died. And it was first identified as a cannibalistically transmitted tendency many, many years ago, which means it's interesting that people then went and did almost the same experiment with cows and were then really surprised when BSE came along. So I would say that actually, from an evolutionary point of view, it is not advantageous to be a cannibal, at least not for humans, and so that probably explains why the practice is so rare.
Well, I guess in some other species, especially if you're a very small animal, which is quite short-lived and disease isn't so much of an issue, if you're really, really hungry, then cannibalism is better than dying of starvation. So things like locusts and things will eat each other quite happily if they're hungry.
Dominic, here's one for you. Roy from Newmarket says, when a meteor falls to Earth, does it break the sound barrier?
Yes, it breaks the sound barrier actually by a very long way. These meteors are typically travelling at 10, 20, 30,000 kilometres per second when they impact the atmosphere. So they'll produce a massive shock wave, and you may hear a bang if the meteor is big enough.
Sonic boom.
A sonic boom, yes, exactly. And in fact, if you have a large meteor such as the one which hit Tunguska in 1909, it was the shock wave that caused most of the damage rather than the object itself. the object would have been only a few tens of metres across, but the shockwave it produced devastated an area of several square miles in Siberia.
I guess the reason why you don't normally hear them for small shooting stars is they don't get far enough down, so the sound doesn't reach you standing on the ground.
Yes, and also they're very small objects, most shooting stars.
Thank you, Dominic. Dave, Kitchen Science, you sort of tantalised us and said you had a cool experiment that's dead simple but a breath of fresh air. What do you want people to do?
Okay, this is ridiculously simple. You don't need any kit which you haven't got on you literally at the moment. All I want you to do is hold your hand maybe 6 inches away from your mouth. Then, first of all, blow on it with your mouth open. So open your mouth up and blow on your hand. Remember that temperature. Now purse your lips and blow on your hand and see if you notice any difference. Then play around with the distance of your hand and see if you can find anything interesting going on.
From protons to photons and gluons to muons, The Naked Scientists. Science that's fundamentally more fun.
And you're listening to The Naked Scientists with Chris Smith, with Dave Ansell and Dominic Ford. We're answering all of your science questions. Guys, can we take a look at this one, which we mentioned at the beginning, which really made me laugh? Warren said, what would happen if I took my fish in its bowl into orbit aboard the International Space Station? Now, assuming that the fish does actually survive the journey up there and it doesn't get upset and all that kind of thing in the water coming out, what would be the implications in terms of physics for a fish suspended in microgravity in its bowl in water? What do we think?
I think you'd have some problems keeping the water in the bowl. Obviously, it would start to slosh about. But once your fish started trying to swim along, of course, fish swim by pushing water backwards, which propels them forwards by the conservation of momentum. And that means that the water will be pushed out of the bowl and the fish will be swimming along in the air. Now, I'm not sure whether a fish could swim in the air in the space station.
I don't think it would move enough air, would it? I don't think it would move enough air.
Someone has built a model fish made out of a giant helium balloon, which looks like a giant fish, and it will swim through the air. So a fish, I think, would swim through the air very slowly. It would, of course, be running out of oxygen very quickly if it did that.
Because I think the water would fragment, wouldn't it? Because the water and the bowl and the fish are all in free fall. In orbit around the Earth. So there's no net force actually applying the water against the bowl, so the bowl pushes back on the water and holds it in. So if the fish sort of disturbs the water enough, all those resonances are going to build up and the water's going to splash out of the bowl, probably in lots of little particles that are then going to blob around in the air in the spacecraft. And that means the fish could end up quite literally out of water, so to speak.
Although surface tension is quite strong, and if it's a small fish, and the surface tension will hold the water in the bowl for quite a long time, I'd have thought, unless you really slosh it about. And if it was a small fish, probably actually surface tension would hold it in the water.
Terrific, thank you, Dave. We got this text in, we don't know who it's from, so here is your answer. How do bats know it's night? Because they live in dark caves. Brilliant question. The answer is it's all down to the body clock. As mammals, we humans are diurnal, we're active in the daytime, but we have in our brains a circadian clock. It's called the suprachiasmatic nucleus that keeps time. It's a few thousand nerve cells, maybe 20,000 nerve cells that are all interconnected, and they're running a genetic program that works a bit like a molecular domino effect. So one gene turns on, it then turns on another gene, which turns on a third gene, and that third gene feeds back and turns off the first gene, and so on. And this molecular clockwork takes about 24 hours to go around a complete cycle. And as it goes around the complete cycle, it's activating the cell in different ways. So these nerve cells become more or less active and they secrete various hormones into the bloodstream, and they go round the body and inform all of the tissues in the body that have their own body clocks what time it is. So you have this master clock in your head and you have these other slave clocks, if you like, in every cell in your body. And that's how your tissues know what time of day it is. And jet lag is all about a disparity between when you really should be getting up and when your body is actually thinking it should be getting up. And you reset that body clock, your brain, suprachiasmatic nucleus, because there is a feed from the retina, your eye, have a very special set of nerve cells called ganglion cells at the back of the eye that can detect blue light, and they send signals into this body clock to reset it so that your body clock is in sync with when it's getting light and when it's getting dark, and that's why you can get over jet lag. But some animals, rather than us who get up when it's light, some animals have reversed their response to their body clock, so when it gets light they go to bed, and when it gets dark, they wake up. And they have all the same hormone signals that we do, they just respond to them in a different way. And mice are the same. Mice are nocturnal, so they go to sleep when it gets light and they wake up when it gets dark, and this is to avoid predation. And bats come out at night time as slaves to their body clocks, and so they're actually using this very ancestral deep body clock inside their brain to work out what time it is. You're listening to The Naked Scientists. We're answering your science questions. It's Chris Smith, Dave Ansell and Dominic Ford. Any question goes, just send them in. chris@thenakedscientist.com is our email address. Scribble on Facebook, we've got a Facebook page, or send us a tweet. @Naked Scientist, you can tweet us. Now, here at The Naked Scientists, we have teamed up recently with the Planet Earth podcast. They're from the Natural Environment Research Council. And we're going to bring you a series of science features which have been recorded on location all across the UK. And our reporters are science broadcasters. They're also BBC presenters. They're Sue Nelson and Richard Hollingham. And for our first report, Richard Hollingham has travelled to the northwest of Scotland.
Waves lapping the beach, wind bending the trees and the tides pulling the pebbles along the shore. Increasingly, governments and energy companies are looking at ways of harvesting this energy. Well, it makes sense. But what about the environmental impacts of marine-based renewable energy technologies? Well, I'm on the beach at Oban in Western Scotland with Ben Wilson from the Scottish Association for Marine Science. Now, you're looking at the impact of these devices. What sort of things harvest the power of the waves or the tide?
Some of them are at their most basic, do look just like wind turbines put underwater. There's other ones that are more complicated with lots of different blades on the rotors, other ones that are like wind turbines in tubes and so on. There's a lot of ideas that people have had, but it's very much a new thing.
Now, we've heard about problems with wind turbines on land and birds. Are you imagining the same sorts of things are going to go on with these turbines underwater and fish or seals or whales?
What we want to make sure is that those devices that go into the sea are the right ones, and that organisms that are already moving around in the sea are not going to come a cropper by bumping into these devices. What we're looking at in particular is they're probably going to hear these devices upstream somehow. How are they going to hear it? What are they going to hear? And are they going to be able to hear it far enough in advance to be able to actually take the right manoeuvring actions to get out of the way?
But before Ben could work out the sorts of noises renewables ought to make, he realised he needed to know what life beneath the waves already sounds like. Back in the lab, Ben played me some of his recordings.
This is a recording I made when I was working on killer whales, and so I was listening away to some killer whales swimming around probably about half a kilometre away from the boat. And somebody way in the distance started a little outboard motor on a little skiff and went driving away and completely drowned out all the recording I was trying to make.
That sound we're hearing of the boat in the distance, would that be similar to the sorts of sounds a turbine underwater might make?
Well, that's what we don't know. This is a new industry. These devices are being built at this very moment, so we don't know what they're going to sound like. And particularly of interest is what they're going to sound like after they've been in the sea for a couple of years. You know, the day they go in, they're going to be nice and well lubricated and so on, but they might become a lot more noisy later on.
So you've got another sound here. What's this one? This is a bit different.
This is two noises that are all pervasive, particularly in this area. The first one is sort of snap, crackle and pop sound, what's commonly called snapping shrimps. It's not quite clear what's making that sound. It's probably a crustacean. If you go anywhere in coastal waters, anywhere in the world, you'll hear this sound. And then the other sound on top of that is another human-made sound, and it's the noise of a seal scare. It's quite high frequency. It's quite common around this bit of the coast.
That's extraordinary that these sounds are recorded underwater. This is the sounds, the things that are happening under the sea that we wouldn't hear.
Absolutely, and the other point to this is that it's different in different environments. If you imagine walking through a wood, you hear different noises as you're near a road or as you're near some trees with the wind blowing through them. As you move around underwater, you get this soundscape of different sounds in different areas.
So how will you use the results of this? Once you've gathered your sounds, how will you use that?
I think the first thing is an appreciation of what it sounds like underwater. We need to get an idea of what the variation is and how it varies between different environments where these things are going to go. And then the second one is we need to make sure that the noises the devices are making will be audible to animals moving through. And if not, do we need to think about adding a bit of noise?
So can we just end with one more sound? What's this one?
Okay, this is an unusual sound that we discovered a couple of years ago and kind of shot us to fame. It's a sound made by herring. We don't know what they use it for, probably communication, but they basically blow bubbles out of their rear end, and in it comes a sound.
And that was the sound of a herring communicating using a fast repetitive tick, or an FRT, fart for short. That ends the first of our features with the Planet Earth podcast. The reporter was Richard Hollingham. We'll be featuring reports and extracts from Planet Earth's podcasts over the coming weeks. You can find out more about their podcasts, and there are some links to them on our website, which is thenakedscientist.com. And if you go to nakedscientist.com/Planet Earth, all the details are there. Dave.
OK, I've got a question for you here, Chris. If you're in a dream and you're running away, is that burning extra calories?
This is from Farah, isn't it? This is on Facebook, on our Facebook page. If you want to type your questions in there, you can, and then other people can comment on them as well. What a terrific idea. It's sort of lazy exercise, isn't it? You sort of lose weight while you're dreaming and sleeping. Well, the answer is kind of yes, to a certain extent. And let me explain why. When you go to sleep, your metabolic rate is lower than it is normally anyway. You go down to closer to your basal metabolic rate because your brain is less active. But it's not less active all the time. And when you actually start dreaming, your brain activity actually becomes very, very high. It's almost, in fact, as active as when you're awake. And so your brain metabolism will mean that because you're dreaming, you're burning more energy for a start. But also, when you dream, there's a part of the brain called the subcerulear region, which is in your brain stem, the thing that connects your forebrain to your spinal cord. And the role of this brain region is to gate or suppress the passage of motor information going out from your brain to your muscles to stop you acting out your dreams. So when you are dreaming about something that involves physical activity, you might have had these dreams where you suddenly think, I feel really weak, I can't run away fast enough, or I can't get away. And there's also a manifestation called sleep paralysis, when people wake up, but this paralysis hasn't been taken off, which should happen when you first wake up, and they lay there feeling seemingly paralysed and can't move for a little while before this brain region turns off. So although you've got this paralysis going on, some of the muscles that you would normally be using to run away or do your thing, whatever you're doing, your exercise in your dream, those muscles might be a little bit more facilitated. They might be more keen to work than they would do otherwise. So you might find there's a slight elevation in metabolic rate because of the dream, but it's not going to be unique to a dream about running. You will burn a few more calories, but just because probably you're dreaming and therefore more active during that phase of sleep. But I don't think you could program or plan to go to sleep and dream intensely about running and exercise and then wake up both fitter and lighter in the morning, unfortunately.
I guess unless you're sleepwalking when it's as good as
well,
the
that's
actual
true.
thing.
That's a very good point. Here's a question from John. Either of you, maybe you, Dave. John wonders, if the world was made of glass, would we be able to see through it?
It's a very good question. Glass is obviously transparent, and so if the world was a beautiful pane of glass, then you can see straight through it. But if you've ever got something made out of glass and dropped it on the floor, shatters into thousands of pieces. If you have a pile of little pieces of glass, it stops being very transparent, although each bit of glass is transparent, because when light hits a surface of glass, some of it reflects and some of it refracts, it bends. So if you have a pile of little rough bits of glass, the light will cut, although it's all transparent, but you get lots of reflections, you get lots of refractions, it all merges together into a kind of white blur. This is why ground glass always looks white.
It's the same reason, I guess, why snow is white and water is transparent.
Exactly, and the same thing with sugar. If you look at a crystal of sugar, that's entirely transparent. And so the Earth isn't very flat and smooth and shiny. Therefore, if the world was made out of glass, it would probably look white.
This is an interesting one. N. Ravinad has said, why is morning breath smelly even after thorough brushing, including the tongue, before we go to sleep? And the reason for this is that when you go to sleep, because, as we've just been saying, when you're asleep, your metabolic rate drops, your activity levels drop, all your body secretions dry up as well. So your eyes produce far fewer tears, your other mucous membranes produce fewer secretions, and your mouth produces far less saliva. And saliva has got two roles. One, it washes away bacteria. And two, it also contains various things, including antibodies and other chemicals, lactoferrin and so on, that suppress the growth of microorganisms. So because you have got less saliva, so things are drier, and because you have got fewer of these antimicrobial components like lysozyme in the mouth, microbes actually tend to flourish more at night when we go to sleep. And the mouth contains a very diverse population of bacteria. There may be 80 more or 100 more different species of bacteria in the mouth, many, many more in some people. And some of those bacteria are capable of metabolizing various sulfur-containing compounds. And from those sulfur-containing compounds, they produce volatile chemicals that are quite whiffy, like hydrogen sulfide. And so you do wake up with a proliferation of these bugs in your mouth more than you would have when you were making lots of saliva. And as a result, they make more of these whiffy chemicals and your breath smells until you do actually drink something to wash them away and also to begin the process of making saliva that then helps to suppress their activity. So that's why. If you've got a question for us, email chris@thenakedscientist.com. Dominic, is the speed of light the same at each end of the spectrum? That's a text message from someone.
If you have light travelling through a vacuum, yes it is. So if you're looking at starlight, which has been travelling through the vacuum of space, all of the different colours of light in the spectrum of that star will have travelled to us at the same speed. But if light is travelling through a medium like air or glass, which presents some resistance to the light, which is to say it refracts the light, it bends the light, then different colours travel at different speeds, and that's why prisms split up light into different colours, because the light is travelling at a different speed through the prism.
Thank you very much, Dominic. And now with a look at another new feature that's kicking off next week, here's Mira Senthalingam.
Coming up next week, we bring you Naked Engineering.
Many buildings are still standing this way, including Clare College Bridge here in Cambridge, which, if you look carefully, is quite distorted because one of the supports on the end has settled quite a bit.
To kick things off, we look into an architectural feat which goes far back into our history, the masonry arch, as we discover just how these structures are built, how they stand up, and the stresses they can handle.
It's quite reassuring because it took me about 2 years to notice the fact that the bridge was completely wonky, despite having walked over that bridge several times a day, every day.
So join us from next week onwards as we reveal how arches are about more than just aesthetics and investigate more landmarks from the world of engineering.
Mira with an update on Naked Engineering, which we're kicking off as a new feature every week here on The Naked Scientists from next week. Hello, Liz.
Hello.
What can we do for you?
Well, I was swimming in the sea recently and noticed that the water had a swirling effect, and right next to where I was standing or any pillars in the water, it was very pronounced, and we were trying to figure out why that was happening.
Dave, this sounds like one for you because I haven't got a clue.
Where were you? Was it a tidal region in the sea? Was there a tide flow?
We're in a little inlet. It's on the northwest coast. It's called the Puget Sound. It is the Puget Sound-ish area.
I haven't quite got in my head exactly what you're saying, but you'll certainly see some swirling effects if you've got the water flowing past a column or something in the water due to a tide. Then you'll see a kind of wake, and sometimes that can be quite swirly. You can also get kind of whirlpools created by sort of tides flying around corners and things, water dropping, being sucked underneath, which actually form quite like it used to be called maelstroms and things, and it can actually form kind of whirlpools.
There's one off the coast of Scotland, which is really outstanding. I can't remember this brilliant YouTube footage. If you type into YouTube Maelstrom or Whirlpool Scotland West Coast, you can see it's amazing.
And there's some quite serious ones in the Straits of Messina I sailed past once, which were quite interesting.
Not into them, hopefully, though.
Which you've got round the side.
Dominic, here's one from Eric Nolan. Would a rogue planet, a planetar, be actually visible? He's talking about planets that can be booted out of their own system and just wander aimlessly through space. How does this happen? Can it happen? And would we be able to see them? Because presumably they don't produce any light.
Yes, we think there are quite a lot of objects like this. We think solar systems form, and then often many of the smaller planets will get thrown out by the larger planets. And one reason why we think that is that a lot of the solar systems that we've seen around other stars have Jupiter-sized planets very close in to their host stars. And it's absolutely impossible to form Jupiter-sized planets there. So these planets must have formed in the outer parts of these solar systems and then spiralled in. And as they spiralled in, they were just throwing out any smaller planets that they spiraled past. So there probably are a large number of lonely planets just lying out in outer space, nowhere near any stars. Unfortunately, they are virtually impossible to see, and we have no idea how many, because there's nothing to light them up. They're cold, they're dark.
And let's hope that they're not heading this way. Dominic, thank you. We're fast approaching the end of the Naked Scientists for this week. Diana O'Carroll will be with us shortly for our question of the week, when we've been finding out what is that funny smell that you smell after it has been raining. It's a very fresh, very distinctive post-rain smell, but what makes it happen? But before then, talking of a breath of fresh air, Dave, your kitchen science for this week.
OK, I ask you to try basically just blowing on your hand. So hold your hand about 6 inches away from your mouth. OK. Sort of blowing at it with your mouth open.
Warm.
Feels warm. Now with your pursed lips.
Cooler.
Much cooler. So there's something strange going on here. Now try blowing with pursed lips, but hold your finger very, very close. Right up to your mouth.
Hot.
Hot again. So there's something strange happening in that distance. And if you blow with an open mouth with your hand a really long way away, this is more difficult.
I can just about feel it.
It's starting to get cooler again, isn't it?
Okay.
I think it depends if you...
I can't feel it. How far away? A foot?
End of arm's length.
Okay, yes. Okay, so it's the same thing that when it's close up actually feels hot, but when you get further away it feels cold again.
Basically, you're producing a jet of air from your mouth going out through the cool, dry air in the room you're in or outside. When a fast-moving jet of air moves through stationary air, it tends to drag the cold air with it. It's called entrainment, and so it entrains air. And that can only happen around the edges. So if you've got a small jet of air going very fast, you get a lot of entrainment. If you've got a big tube of air going slowly, compared to the amount of air you've got much less entrainment. So the small jet of air entrains air very, very quickly. So all you're left with is fast-moving room air, basically. Because it's moving fast, it increases evaporation on your fingers. Like I was talking
It feels colder.
And it feels colder. But if you've only got a mouth open, mostly what gets there is the warm air from your mouth. So it doesn't feel very cold, it still feels warm.
It's amazing. So it's a vortex effect. It's the same thing, because we were talking about, there was a beautiful paper published earlier this year looking at how fungi get their spores sufficiently high above them so that they then end up in the jet stream, so the spores are carried a long way away so they'll land elsewhere. No, not fungi, moss. And the wonderful discovery was that they do this by generating a little puff of air in such a way that it propels them so fast that it creates a little vortex effect, and this helps the spores to travel much further, in fact I think about 100-200% further than they otherwise would.
Yeah, it's all about dragging lots of air, and then you've got lots of momentum, which keeps it going.
Fantastic. Dominic, this one probably is a good one for you. Kieran Lowe says, considering the theory energy cannot be created or destroyed, what happens, for example, to the energy of a coiled spring which is placed in a pot of acid?
Well, when the acid dissolves, obviously the spring will break and it will dislodge the acid in the pot. And that will create turbulence inside that acid, and that will ultimately be dissipated as heat. So the acid will get slightly hotter.
Or even the atoms inside the spring, because they're being stretched, they're at a slightly higher energy, they've got slightly more potential energy. So chemically, when something rips them off, it'll take less energy to break that bond. So there's less energy lost when you break the bond, so more is left over when it reacts with the acid, so you get more heat.
Now, Steve's being a bit provocative. He's got in touch on the text and says, apart from the obvious military use of the moon, what is the point of space exploration? What do we think of that?
Well, I guess it's driven a lot of technological advance in the last 30 years or so. I mean, the Apollo missions certainly inspired people to create a lot of technology that they wouldn't have created otherwise.
And GPS is really useful, and we've found an awful lot about the Earth. Like, you can send satellites up to find out where the forests are. There's a huge amount we can learn about the Earth from space.
And Wi-Fi is entirely based in terms of its protocols on radio astronomy. Couldn't do it without that. And the World Wide Web, without CERN, for example, and saying we're going to have a big particle accelerators and all these big projects. We need ways for physicists to talk to each other. That directly catalysed the development of HTML, the language that made the web possible. So I think there are all these other spin-offs that we basically can thank these technologies for. So I think it's worth doing, if nothing else, for the spin-offs.
Plus just the finding out what's out there.
Indeed. Thank you, Dave. Let's join Diana O'Carroll now for this week's Question of the Week.
This week we've been enjoying some typical British autumn weather. Rain.
Hello, this is Julia. I'm from Edinburgh, and I was wondering, what's that distinctive smell after it rains?
So what gives rise to that damp, earthy smell when the ground around you is damp and earthy?
I'm Beryl Zaitlin. I'm adjunct professor at the University of Calgary. Well, I looked it up, and the actual answer is we really don't know. Because odor is something that has to be a volatile chemical of some sort. It's a compound that goes to your nose, and the receptors in your nose absorb that chemical. So it has to be some sort of chemical that's in the air. In the 1960s, two researchers, Baer and Thomas in Australia, extracted some oil from clay, and they thought that oil had a biological origin, and they thought it smelled like the smell of rain. And then that was all the research that was done on it for 10 years. And then in the 1970s, Nancy Gerber, who was one of the very prominent researchers in taste and odor, isolated 3 chemicals from actinomycetes.
Actinomycetes are bacteria that live in soil and break down plant material like leaves and twigs, making compost.
And one of those chemicals was 2-isopropyl-3-methoxypyrazine, which is what she thought Baer and Thomas had originally isolated. And it was a chemical that smelled like rain. And she published that she thought this might be the chemical that made the smell of rain, and she thought it might have been the chemical that Baer and Thomas had isolated. And that was it. Nobody's done anything since, as far as I can tell. It might be that the smell of rain comes from actinomycetes, and it might not, and at the moment, nobody really knows, as far as I can tell.
So it could be that these bacteria are producing the smell, but the odour jury is still out on this one. We had some suggestions on the forum, including Tay, who said it could be plants emitting lots of gases when they get wet and their pores open. And our Forumer of the Week award goes to Variola, who identified the smell as geosmin, an organic compound which bacteria, the actinomycetes, produce when they die, usually after the soil has been disturbed or it's rained following a dry period. And geosmin is one of the other chemicals that Nancy Gerber, whom our expert answerer mentioned, isolated when tracking down the earthy smell. But from the essence of soil bacteria to the essence of olives, with a question from David Karma.
Hi. For quite a few years now, we've been using olive oil-based butter in our household because we've heard of claims that since olive oil is healthy, then its butter and margarine-based counterparts are healthy as well. Does the claim still hold true that olive oil-based butter and margarine are healthier than their dairy or coconut counterparts? Thanks.
Is olive oil really better for you? And why might that be? Answers on our forum at thenakedscientist.com/forum or email chris@thenakedscientists.com. Incidentally, there's still time to take part in our survey and win Amazon vouchers worth £10 or equivalent currency. We've got 10 of them to give away by the 10th of the 10th, 2010, and we'd like to know who is listening to us and what you think of our shows. You can find the survey at thenakedscientists.com/survey.
Diana O'Carroll with this week's Question of the Week. You can also catch up with previous episodes of Question of the Week on our website at nakedscientist.com/QOTW or look it up on iTunes. That's all we've got time for this week. Thank you very much for joining us on our question and answer extravaganza. In the hot seat next week is Ben Valsler, who will be here to bring you an update on the goings-on at the British Science Association's Festival of Science, which is taking place this year at the University of Birmingham. So he'll come back with a roundup of the best of the fest. In the meantime, if you'd like to get in touch with us, then do send your questions, thoughts and feedback to me, chris@thenakedscientist.com, or join us on our website forum at nakedscientist.com/forum, where you can ask and answer science questions from people all over the world. Right now, I have to say a very big thank you to our wonderful production team. They are, in no particular order, Dave Ansell, Dominic Ford, Julia Graham, Smita Mundasad, Sarah Caster-Perry and Tom Simpkins, and of course our very own Ben Valsler. Have a very nice week and see you next time. Goodbye.
The Naked Scientists comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the Natural Environment Research Council and UK FAST. For more information, look us up online at nakedscientists.com.